some differences between these machines. Firstly, on the Blue Gene, the first machine with hardware transactional memory, it was impossible for programmers to write the handlers for failed transactions. Recall, instead it is retried until a certain number of transactions have failed, and then this transaction tries to get a lock so that when it has this lock, it is guaranteed to succeed. Okay, and more also for the Blue Gene, there are system calls to begin and commit a transaction. And the other machines use normal machine instructions, which of course is much faster. For the mainframe EC12, the cache block size is quite big. And the risk with this is that there can be conflicts by transactions that access different variables which happen to be located in the same cache block. So that's we will come back to this both in this lecture, but also in the lecture about cache-aware programming for multi-cores. Okay, so the EC12 and the Intel both use the L1 cache to detect conflicts, and for the machines, when the transaction capacity is exceeded, the transaction is aborted, and then it matters how big this capacity is. And as we will see, the power 8 has the smallest capacity of writing speculative state. It's not public for the Intel machine, but the IBM researchers made some experiments and figured out that it must be 4 megabytes for reads and 22 kilobytes for writes. The Power 8 has only 8 kilobytes in total for reads and writes. Okay, so here we can see some parameters, how they differ, and the level of simultaneous multi-threading is quite different, and also the cache block size and the capacity of speculative state. It's biggest on the Blue Gene and smallest on the Power 8. So some interesting parameters for these machines are collected here, and we can see that the mainframe is the fastest, at least the clock. To make these comparisons fair, all machines in the experiments use 4 cores, and the experiments are not against different machines, but I mean between different machines, but instead, well, there are, but the measurement is speed up versus one thread on the same machine, so not absolute time. And the purpose is not to say that this machine is the best, because they are on completely different markets, but instead to understand how to improve transactional memory implementations in the, future implementations. Okay, so 4 core speed up versus itself. What can we see? Okay, some have, I would say that they are not so very different. On the different machines, they are quite closely related, and it matters more about which application they run. Okay, I will not go into details about this, but what we will see is the reason for transaction failure, which differs. And one reason for the Intel machine getting quite the number of transaction failures, despite the small cache block size, is that it has hardware prefetching. But what is that? Well, it is that the hardware discovers that, for instance, the program accesses elements in an array, and if it sees that, okay, now it has used 2 or 3, actually 3 cache blocks in sequence, or with the same offset between them, then the hardware can guess that the program probably will use the next suitable cache block as well, and starts prefetching it by itself. Okay, and a mistake by Intel is that these are counted as transaction accesses, but it's not really access by the transaction, since this is just a hint to the cache that it should prefetch the data. Okay, and for one of the applications, this one, K means low, we can see that the Intel, no, not there, but here, the Intel machine here, it had lower speed up than, well, to some degree on this benchmark, but we can also see it in more particular on that there were more failures, although there were not so many, so they didn't impact the execution time and therefore the speed up on the previous slide. But this is one explanation to why there were more failures for some applications from Intel. And what's interesting now is that the IBM researchers disabled this hardware prefetch and informed Intel, and they confirmed that this is how hardware transactional memory was implemented in the Intel machine. Okay, what we more can see is that the Power 8 had well, it has a small capacity, so there are more failures, and that's that's a reason for increasing the capacity on future power machines. And now there is an interesting remark, namely that this machine suffers from mysterious transaction aborts that degrade its performance. Okay, so what is meant by that? It's simply they couldn't figure out why, and the reason is that the failure codes were not documented and happened in odd situations, and then it makes it super complicated to figure out what actually had happened. So good error codes from the hardware as to why a transaction fails is really important, both for hardware developers to understand what they should improve for the next machine, and for programmers to avoid these failures. But this is a nicer way to write this than didn't do it due to lack of time, which is just crap. Okay, so let's look at this. Well, mostly it may not always be crap to say that you don't have time, but this is a more serious explanation in my view. So let's look now at the fraction of started transactions which abort. So this is really, in some sense, the bottom line of how good hardware transactional memory is. Because if they usually fail, then there is a big problem for everyone involved. But as we can see here, for many of the programs, most of the transactions succeed. And it's not very interesting to see exactly why this application or that application. Well, if you want to really study this, then of course you should do that. But we can. That's not the purpose of this lecture. It's just to make a general overview to see how good they are and what happens. So we can see that for this benchmark, it's in particular for the power 8 capacity overflow, which limits the success rate of the transactions. Okay, so I would like to make a last remark about, maybe not last, but another remark about hardware transactional memory. This is just my prediction, and it is that since it's easy to implement, given that the machine already has L2 caches, which they obviously have, and cache coherence protocols, then it's a quite small addition. So I think this will be more and more widespread, and it's already in machines from IBM, Intel, AMD, and ARM. Okay, and as you will see when you do the lab, it is seriously more easy to parallelize programs with transactional memory. Okay, but of course, let's go back to this. How much faster does it get? So the question, of course, is this sufficiently fast for the invested time in programming? And also, there is a risk that the transactions start to fail too many times. Okay, this is not looking good for this. So maybe you have a parallel program and everything looks like this and everything is fine, you think. And then your program is run with other input that results in this. Then it may be a sad thing. So there is a risk with transactional memory, but if that can be covered with testing methods, etc., during software development, then I think this is a really nice thing, since it avoids lots of troubles and lets the programmer focus on performance optimization instead of orchestrating the different threads for correctness.